Thank you. Thank you. All right. Can everybody hear me okay? Like this? Awesome. I'm not used to using a microphone. I'm going to talk to you today about galaxies during the epoch of reionization. Very briefly here, the epoch of reionization, what I mean by that is a period in the history of the universe starting about 500 million years after the Big Bang and extending to about 1 billion years, during which all of the hydrogen gas between galaxies in what we call the intergalactic medium was fully ionized. So as part of this story, I'm going to talk about, how we ionize hydrogen, and then I'm going to jump straight to how we ionize the entire universe, because if you're not going 0 to 60, what's the point? Then I'm going to talk briefly about how we actually detect galaxies during this time, and a little bit about what we can learn from them, but it'll really just be the tip of the iceberg. So we're going to start with the hydrogen atom. You've got your proton and electron. In reality, though, it's a little bit more complicated than this. So if I increase the complexity of the cartoon, we have an electron which is capable of taking on multiple different energies, but it can only take very, very specific energies. It can exist in what we call energy levels, not in between. Now, it can jump from one energy level to the next, or it can jump entirely out of the atom by receiving an energy boost. Now, that energy boost can come in many ways, but the most common way is by when the hydrogen atom absorbs a photon. So here's our photon. The photon comes in, a particle of light with some energy. It comes in. If it has enough energy, it will kick that electron out of the atom, and now we've ionized hydrogen. So we've got a free electron and the proton by itself. However, the flip side can also happen. If there's a bunch of free electrons around, one of them will recombine with the proton and release the equivalent amount of energy in the form of a photon. So if you want to keep hydrogen ionized, you have to have a lot of photons around that are energetic enough to keep kicking the electrons out. Let's see. The same process can happen without kicking the electron out. If the photon that comes in doesn't quite have enough energy, but it does have exactly the right amount of energy, it can kick the electron from one energy level to another. Then, because hydrogen atoms are lazy, just like me, that electron wants to fall right back down to its ground state, and it will do so very quickly, and it will release a photon of the same energy, the energy that is the difference between these two levels. So this complicated thing, don't worry about it, is just to graphically represent a bunch of different transitions that can happen in the hydrogen atom. They're going from one energy level to another, or they're going from one energy level all the way out. And so the only ones to really care about right now are the ones that are going from the ground state of hydrogen to other energy levels. And the reason for that is that most of the hydrogen in the universe is in the ground state. If it's neutral, it exists in the ground state because, again, it's all lazy. So the two sort of transitions to keep in mind are the ionization transition, so that would be going from the ground state all the way out of the atom, which requires 13.6 electron volts. That's how much energy you need to ionize hydrogen. And the other transition I'll be talking a little bit about is called Lyman alpha, and it's the transition between the first energy state and the second. And the only thing to really keep in mind here is that these two transitions happen with photons that are very, very high energy. So they happen in the ultraviolet part of the spectrum. They have high energies, so they have blue colors. Let's see. Another tool that we need to understand this, to approach this topic, is the idea of cosmic redshift. So you're all familiar with redshift in some form or another. If you picture when an ambulance comes by you or a fire truck, and the sound changes as it approaches you and it leaves you. That's the same concept here. But in this case, we have light being emitted by a galaxy, and we're receiving it at Earth. And the light, in this cartoon, we've spread the light out through a prism, and there's some spectral feature here. In this case, it's an absorption line. Doesn't matter. But if the galaxy is moving towards us, you can think of this as the light being squashed. So the wavelength of the light shrinks, the wavelength gets shorter, the color gets bluer. And so that's called blue shift. If the galaxy is moving away from us, the opposite happens. The light is getting stretched, and the features are getting shifted to longer wavelengths, which have redder colors. It's getting red shifted. Now, because the entire universe is expanding, all the space is expanding, almost all galaxies are actually moving away from us. Not all of them, but almost all galaxies are moving away from us. And the farther away a galaxy is, the longer the photons that it emits have been traveling through this expanding space, and so the more redshifted they become. And that allows us to map from redshift to the distance of the galaxy. And because when we look further away, we're also looking back in time, redshift is related to both distance and time. But of course, because it's astronomy and nothing is ever simple, it's related in a very non-intuitive way. So this is just to show you, we've got some redshift and time, billions of years since the Big Bang. So we've got today right here with a redshift of 0 and roughly 13.8 billion years past the Big Bang. You can see that by redshift of 1, we've already covered more than almost half the age of the universe. So that makes no sense. But whatever. And so I always have to come back and look at something like this to jog my memory on what redshift and distance actually mean here. So with that under our belt, we're going to talk about the history of the universe in 1 minute-ish. But really just the history of the early universe, because that's what I study and care about. So after the Big Bang, the universe expanded very rapidly, and it was comprised of sort of this soup of particles. There were protons, electrons, and photons all mixed together. And at a certain point, the universe had expanded enough, then cooled, it's cooling as it's expanding, that the protons and the electrons could combine to form hydrogen, and that's called recombination right here. And then what followed that was a period called the Dark Ages. There were no real sources of light. It was just a bunch of hydrogen chilling as the universe continued to expand. And some overdensities of matter started to collapse through gravity and form some structures. But in general, it was, nothing exciting was happening. Then at a certain point, about roughly 300 million years after the Big Bang-ish, everything in astronomy is ish. The first lights turned on, the first stars started to form. And with them, with the light, the photons that they were emitting, they started to create energy. And that energy could ionize the hydrogen around it. So we start getting these little sources surrounded by these bubbles. And as time passes, more lights turn on, more bubbles form, and they start to overlap. It's a little hard to see on the screen, but they start to get bigger and bigger and overlap until eventually the entire space is ionized. And that period is called reionization, and that's the period we're talking about today. And then, the rest of the history of the universe happened. Cool. So I'm talking about the period when the universe was just about 500 million years to 1 billion years old, and then the other 12 billion years, whatever, just move on. Okay, so that's what we're talking about today. And this is, excellent, it's playing. So this is a simulation helping us visualize what we think reionization looks like. So the dark clouds here are neutral hydrogen. The lighter stuff is ionized hydrogen. And as we fly through the intergalactic medium, the hydrogen is being ionized, so that the dark stuff is disappearing. And as you can see looking at this, it's not a uniform process. It doesn't all happen at once. It doesn't happen smoothly. It happens around little regions that grow and expand. And astronomers I would love everything to be simple. I would love if it was just a spherical bubble that expanded. But you can see here it's patchy and it's messy, and that makes it very, very difficult to observe and to understand what we're observing. So I'm going to next now talk about how we detect galaxies during the epoch of reionization. Some of these techniques, they're not specific to the epoch of reionization, but there are some observational signatures that are specific. So what I've shown here is the model spectrum of a galaxy. So this is the wavelength of the light and the brightness of the light. This is just a model of a galaxy based on some that we've observed more locally. And then this is what that galaxy would look like if I put it at a very high redshift, if I put it into the epoch of reionization. What's happened here is two things. First, the light has been redshifted. So light that was over here, and it was kind of blue, it's been stretched all the way over here to redder wavelengths. The other thing that's happened is that the universe is, during reionization, is partially neutral. So the electrons are still in the hydrogen atom. When the photons come by, they get absorbed by the neutral hydrogen. And then we don't see them anymore. They're absorbed from our line of sight. So the brightness of the galaxy has gone down. And I've put these two stars here to show you. This is a part of the galaxy, and this is a part of the spectrum, and this is the exact same part of the spectrum at high redshift. So you can see that this point, this feature, has gone to redder wavelengths, and it's gone to lower fluxes, lower brightnesses. However, that allows us to use, you'll notice that all of this brightness has disappeared. It's been absorbed. But that allows us to be able to detect galaxies based on this fun shape that they have. We call it the Lyman break. And we can observe them by seeing how bright a galaxy is over here and how bright it is over here, and seeing if we can detect this break. So to show it a little bit clearer, here is a cartoon. We're looking at the model of the galaxy, and we're looking at the images of that galaxy as it goes to higher and higher redshifts. These images are taken in these filters, and we see that, let me see if I can go back and show it again. No, we'll just stay here. That's fine. So you've seen that it started out in all the images, and it slowly dropped out of all the images. We can only see it now at the highest redshift. We can only see it in the reddest filter. So that's a model, that's a simulation that's showing you what's going on as an illustration. Now let's look at some real data. Oh, there we go. We can watch it again. Yeah, so all this blue flux is being absorbed, and everything else is being redshifted. Okay, so here's some real data from the Hubble Space Telescope. We've got 3 different galaxies in 4 different filters, and the filters are going from blue to red. So, I like to say, you know your astronomer when you can find the galaxies, because only an astronomer would look at this and say, yeah, that's definitely a real thing. So just to help your eye a little bit, there are some circles, but you can see that we've detected the galaxies in these bands. There may be a little bit of a detection here, but then they're missing, and that's actually something different. Then they're missing. Like I said, it's not a smooth, easy process. They're missing, and so what we're seeing here is that break in the spectrum. These galaxies are actually at a redshift of 8, 9, and 10. So very, very far away, when the universe was about, 600 million years old, maybe a little older. So another way to detect another way to detect galaxies is by their Lyman alpha emission. So remember that toy model of the atom, or hydrogen atom, and we've got an electron that's jumping from the first energy level to the second, and then because it's lazy, it falls back down and it releases a photon, and that photon between these 2 levels is called a Lyman alpha photon. Their Lyman alpha photons are produced in massive quantities in star-forming regions in galaxies. The reason is that very, very massive hot stars produce a lot of high-energy radiation that gives energy to these electrons and either excites them or kicks them out. And those electrons want to fall back because they're lazy and release these photons. So we get a lot of these photons from star-forming regions. And this is spectra of 2 galaxies at redshift about 6.5, which is during the epoch of reionization, when the universe is about 1 billion years old. We're looking at the wavelength and the brightness again. And so this is just to illustrate 2 examples. There are many, many more, but 2 examples of what Lyman alpha emission looks like. Just an emission line. Okay, so... However, If you've been, you might, as I say this, you might think, well, wait a minute, these photons are likely absorbed by neutral hydrogen because they're, there's neutral hydrogen during the epoch of reionization. These photons are very susceptible to being absorbed by that. So what's going on? If we're detecting a lot of galaxies in Lyman alpha emission, what does that mean if the universe is still neutral? Well, it could mean a couple of things. It could mean that it actually isn't still neutral. It could mean that we're looking at galaxies in regions that have already ionized. We could be looking at galaxies that already exist in these bubbles, so their photons can escape to get to us without being absorbed. And that would be cool because it would mean that we're observing the bubbles of reionization. And that would be very exciting. However, of course, it's not the only possibility. The other possibility is that the galaxies are surrounded by neutral hydrogen, but the Lyman alpha photons can escape some other way. One possible way they could escape is through outflows. So you could have something like a supernova or some other massive explosion or outflow in a galaxy that creates holes and just blasts the hydrogen gas out, and then the photons can escape through the little channels of ionized gas. That's one possibility. Another possibility, and again, there are more than this, I'm just touching on a couple, is that the photons could be redshifted. And I'll explain what I mean by that with another super awesome cartoon. So, now imagine that you have some sources that are creating energy, creating ionizing energy. They could be stars or galaxies. They exist in some bubble that's ionized, and they're surrounded by neutral hydrogen. Now, if we were just looking at them intrinsically without all of this other business going on, we might see, if we were to look at their Lyman alpha photons, and again, this is wavelength and brightness, if we're counting up the photons, we might see something that looks like this. But when we actually observe these galaxies, we see something that looks more like this, way too complicated. It's got double peaks, it's asymmetric, it's like there's this dip in the middle, none of this is good. So what's going on here? So one thing that's going on is that there are a bunch of photons that are that have exactly the right energy to get absorbed by neutral hydrogen. So they have exactly the right energy to get that electron kicked up a level. And so we get this dip right in the middle. The next thing that happens is that some of the photons that are on the bluer side, so this is bluer and this is redder, so this is shorter wavelengths and longer wavelengths. So a bunch of the photons on the bluer side, maybe they can escape through some of those holes that we talked about earlier. Somehow they manage to get out of the galaxy without being absorbed. So they create this little peak on the blue side, and some photons get redshifted. So what happens here is photons that are emitted on the blue side, they might go, and instead of getting straight out of the cloud, they sort of bump around a bit. They bump into a hydrogen atom over here, and they get absorbed and re-emitted. They bump into a hydrogen atom over here. They get knocked around. They sort of random walk their way through the cloud. And as this is happening, the universe is expanding, and the photons are getting redshifted. So by the time the photon reaches the edge of the cloud, it has been redshifted far enough that its energy is no longer high enough to kick that electron up a level, so it just passes right through without being absorbed. And that's why we get this sort of long tail of red photons. So we have this fairly complicated profile that we expect to observe from galaxies, but what we find is that galaxies during the epoch of reionization actually look like this. This is, again, two examples of, when I say many, there are probably like 12. No, there's more than that, but really it's not that many. And so what we see here is, in both cases, we've got the red peak, but it just cuts off and all of the blue photons have been absorbed. And that's interpreted as a signature that these galaxies are surrounded by neutral hydrogen and these blue photons are not able to escape. However, it would be really great if we could, we're limited in what we can learn. We're limited in what we can learn from these galaxies because we're missing so much information. We're missing more than half of the Lyman alpha photons that these galaxies create. It would be great if we could get that. Also, it's really hard to get this kind of data at that high redshift. You have to sit on a telescope like the Keck telescopes, you have to sit on these things for 12, 15 hours, and that's very expensive. So if we want to learn about what's going on here, we have to turn to the local universe. And so what we do is we take galaxies that are much closer and much easier to observe, and additionally are not surrounded by neutral hydrogen. The galaxies close to us are in the IGM, the intergalactic medium, that's all ionized. We study them and we look at their Lyman alpha profiles. So these are the green P galaxies. I think we've heard a talk about them in the past here. They were actually discovered by citizen scientists doing a Zooniverse project. They're very, very cool galaxies that are emitting a lot of high energy radiation. And this is a collection of their Lyman alpha line profiles. And so we can see the double peaks, and we can see the asymmetry. And what's interesting about these plots is that they're ordered from the galaxies that have the least amount of ionizing radiation that's escaping the galaxy to the ones that have the most. So there's a rough correlation, an astronomy correlation, you know, an astronomical correlation, which means take it with a grain of salt, between observing this blue peak and expecting that you'll be able to detect photons that are capable of ionizing hydrogen from coming from these galaxies. Another way to show that is here. So these are actually not the same galaxies, but a related sample where we have the escape fraction of ionizing photons and the escape fraction of Lyman alpha photons. And again, they're correlated by an astronomer, you know, this is what an astronomer would call a correlation. So what this means is that even though it's really, really hard to observe the galaxy, to observe this type of detail for galaxies at redshift 6, 7, 8, 9, we can, if we are able to observe their line profiles with, for example, the James Webb Space Telescope in a couple to 10 years. If we are able to do that, then we might be able to interpret these local observations to help us understand what we're seeing at high redshift. And as a last example, these are two galaxies that are detected at redshift 6, around 6.5, so about 1 billion years after the Big Bang. One of them has just the red peak with all the blue photons absorbed. One of them has a double peak. And so we can maybe interpret this as meaning that this galaxy, even though the intergalactic medium still is partially neutral, this galaxy is in an ionized bubble. That, or it has outflows or some other way to let the Lyman alpha photons escape. So we still have a lot of degeneracies that we have to break with this story. So just to briefly conclude the story, my conclusions are in two parts. The first part is just to remind you what sort of happened here, talking a little bit about ionization of hydrogen, talking about how we can detect these galaxies, and then talking about if we are detecting Lyman alpha from galaxies, it could mean that they are in a neutral region, an ionized region, but it could also mean that the photons are able to escape through some other way. And as a second part of my conclusions, because I always learn better from videos, I'm going to show you a video covering the concepts of reionization. I cannot claim credit for the music or the idea, but the words are mine.
All right, thank you, Deep Space Shine. So the way this will work, if you have a question, raise your hand. When I call on you, ask the question. Hopefully one of us will remember to repeat the question, and then Deep Space Shine will answer it. So let's start with you right up here.
Evening, Space Shine. Lovely talk. Got as much of a comment as anything else. I was noticing that the profile of the peaks look very much like the top half of the sine wave. And what happens when you reach the Lyman alpha line looks very similar to what happens when you pass the sine wave through similar filtration, band pass, band stop, et cetera, et cetera. And I'm kind of wondering if there is some kind of a correlation there.
Yeah.
There's another correlation that's been made in history, like James Maxwell and electromagnetism, et cetera, et cetera.
Sure.
I'm curious if there's one any lighting and electricity.
Yeah, so the question, correct me if I rephrase this incorrect. The question is, so the Lyman alpha line profile looks a bit like a sine wave, and can that tell us anything about what's actually going on? Is there a relation there? And I think, honestly, I think I simplified what the profile looks like a lot. It doesn't actually, in reality, look much like a sine wave, but that was a lot easier to draw in my cartoon. So there are more like 5 or 6 peaks that are sort of spread out. There's like there's 2 blue peaks and 3 red peaks, and they all have different waves. They all have different heights, and then there's a bunch of long decaying wings. So I'm not sure how to answer your question. I don't know that I would know exactly how that's correlated, but it is interesting that every single piece of that profile can tell us something interesting about how the photons got there. So it'll tell us how far they traveled, how far they were redshifted, how far they were scattered, whether they encountered hydrogen or dust or were somehow otherwise absorbed. So there's a lot of information in that profile, and I massively simplified it because I can't draw.
We have a Twitter question. So this comes from Geta, and Geta, during intermission, find one of the hosts. We will have something for you. But she asked, she would like a little bit of clarification on that complicated, non-intuitive connection you made between redshift and time. She asks, what does it mean to have something be more redshifted? So can you kind of remind us what this redshift scale really is telling us?
Sure, I can try. So the redshift that we're talking about here is cosmic redshift. It's not Doppler redshift that you get from an ambulance or from observing planets. This is cosmic redshift, so the redshift is caused by the expansion of space. So the expansion of the universe is stretching the light to longer and longer wavelengths. So if you take a galaxy that's very close to us, the light leaves the galaxy and it reaches us in, 100 million years. That photon only had 100 million years of stretch. If you take a galaxy that's 13 billion light years away, that photon spent 13 billion years being stretched by the universe. It is going to be much, much, much redder, much, much further redshifted, and that's how we know that it's much further away. Hopefully that helped.
Yeah, redshift, distances are notoriously difficult in astronomy. So the more redshift that occurs gives us a sense of how long that photon has been traveling.
And I look at that chart every day to try to remember how it maps.
Right, it could be like a factor of 2 or something, but it's weird and nonlinear and who knows. All right, we have checking up on the balcony. Okay, we'll do a balcony question and then you. So balcony question.
When you say galaxies in this effort, are we talking like with potential solar systems and maybe even planets, or is this a looser definition of galaxy?
That's a really good question, and I'm going to stay as far away from planets. Oh, sorry, repeat the question. So, thank you. When I talk about galaxies during the epoch of reionization, am I talking about fully formed galaxies that may have solar systems and planets, or do I have a looser definition of galaxies? And the answer is that we're not quite sure. That's a huge question we're trying to answer. These are very, very young galaxies. The universe is very young. It hasn't had time to form much. I don't know much about planet formation. I'm going to let the next speaker maybe address that. But these, some of these galaxies could be, they're certainly forming stars, But beyond that, we don't know much. They might be very, very small and compact single star-forming regions. They could be kind of clumps of star-forming regions. We don't expect them to be as evolved as the Milky Way with these giant spiral arms. We do expect them to be simpler than that, but we don't really know.
So is it expansion in reducing the density that prevents recombination in any hope there?
So the question is it expansion and reducing the density that prevents the electrons and protons from recombining? And it certainly, that has a huge part to play in it, but there is still this background radiation that is energetic enough to continually ionize hydrogen. So some sources are creating radiation and maintaining this ionization process, and that's still an open question as to what those sources are and how powerful they are. That's a really big unknown still.
That was going to be my question, as is it the first stars, is it gamma ray bursts, is it black holes? Have we yet figured out where the primary source of these ionizing photons are coming from? But maybe not so much.
I think, and the answer still, so that is an ongoing debate, and I would let people come down on different sides, and you'll notice that I very carefully avoided making any mention of anything, but it could be, it could be the first stars, the very first most massive stars that formed. It could be just galaxies. It could be galaxies with the additional boost from active galactic nuclei and the ionization as material accretes onto the black hole. It could be any of these things, and we still don't really know, but everybody has an opinion. I think it's galaxies mostly.
And I think it's the first stars, because that's what I study. But who knows? Let's give another round of applause for Deep Space Shine.
Thank you.